Welcome to EarthConsole, the platform that simplifies Earth observation data access, processing, and analysis. Whether you are a researcher, a student, or a service developer, EarthConsole is here to help you use Earth observation data for your project. Let's get started. This video has 5 parts. We'll start by introducing EarthConsole. Then, we'll dive into the platform's parallel processing service. After that, we'll provide an overview of the principles, techniques, and applications of the Differential SAR Interferometry. We'll then provide a demonstration of the P-SBAS for Sentinel-1 on-demand service on EarthConsole, a service developed in collaboration with the Italian Institute for the Electromagnetic Sensing of the Environment. And finally, we'll cover how to request free access to the P-SBAS for Sentinel-1 on-demand service via the European Space Agency Network of Resources initiative. EarthConsole is a platform developed and managed by Progressive Systems, helping the scientific community work with Earth observation data. With EarthConsole, you can get access to different sources of Earth observation data, such as the Copernicus Sentinel missions, ESA scientific missions, or heritage missions, which are missions that are no longer active in space, but which have acquired important data to understand the evolution of natural phenomena over time. EarthConsole also offers flexible environments for developing and testing algorithms and scalable processing capacity to handle large volumes of data with a wide variety of processors provided by important research centers, institutions, and universities serving different scientific purposes. These processors can be used to perform bulk processing, where our experts will run scalable processing campaigns covering extensive geographic areas or long time periods, based on your requirements, and will deliver the processing results to you once ready. Or the processor can be used to perform on-demand processing. Via graphical user interface, you can run your processing tasks autonomously by selecting your area and time period of interest, by configuring the processing parameters, and by downloading results once ready. We have a list of processors hosted on EarthConsole serving different applications available for bulk processing, on-demand processing, or both. In this tutorial, we are going to focus on the P-SBAS for Sentinel-1 on-demand processing service. Let's start with an introduction to the principles, techniques, and applications of Differential SAR Interferometry.
Okay, thank you for your introduction. Hello, everyone. So in this very little time that we have, just 30 minutes, I'll try to explain you and to give you the basic principles of the synthetic aperture radar, and in particular, I will focus on differential synthetic aperture radar interferometry. I'm an engineer, as Alessandro said, in the telecommunication engineer, and I work for developing algorithm of differential SAR interferometry. And so I think that we can move to the first slide of this presentation that, as you can see, is very, very easy slide, because essentially I want to summarize with these 3 fundamental aspects, the 3 fundamental points of the synthetic aperture radar. Okay, that with respect other sensors, the SAR is an active sensor, and after I explain you how it means, it is a microwave sensor, and after I show you how it works, so an important aspect is that the synthetic aperture radar is a coherent sensor. So let's move to the first point. Probably you know, but essentially when we say that it's an active sensor, we want to make a difference between the infrared optical sensor that usually use the solar radiation, in other words, the light as source of illumination, and so the sensor catch the eco ECOS, electromagnetic ECOS from the ground surface. So this means that this kind of sensor can works only during the day. With respect to the synthetic aperture radar, in general, the radar that is itself source of illumination. So the radar shoot on the ground electromagnetic wave. Okay, so the electromagnetic wave strikes the ground, and the radar catch the ECOS, electromagnetic ECOS, with the antenna. This means that with this kind of radars works not only during the day, but also during the night, because they don't need of solar radiation. Okay, so it works 24/7. Another important aspect is that this kind of sensor works in a microwave, with microwave. So in this slide, I want just to make an example of the difference between an optical sensor and a radar sensor. On the left, you have an image. We have two images in this slide. On the left, an optical image acquired simultaneously with the radar image, okay, over Sicily region in Italy, and in particular over Etna volcano. As you can see, with optical image, we have a big problem because we have a big cloud covering the Etna volcano. On the right, we have the radar image acquired simultaneously that, as you can see, the cloud is not present here because the microwave is able to go through the cloud. So we have an information not only with radar 24/7, but also with different weather conditions. Okay, so with rains, cloud, and so on. So it's a very an important aspect of these kind of sensors. We talk about synthetic aperture radar. It is important to understand what is the difference between a synthetic aperture radar and real aperture radar. About the real aperture radar, we have, for example, here a satellite with a radar and antenna, okay, that want to acquire an image of a different target of the ground. It is possible to, with a very easy calculation, to estimate essentially the resolution that this radar may have, okay, on the ground, the resolution delta X, that is connected to several parameters of the antenna and other geometrical parameters. In particular, it's directly proportional to the distance between the antenna and the target on the ground, that is R. Then we have a connection with the wavelength of the radar, and with, as you can see here, L, that is the real length of the antenna. If we work with the satellite synthetic aperture radar, this kind of parameter, R, the distance, we are talking about of 800 kilometers. The wavelength is more or less few centimeters, and the length of antenna, of a real antenna, is more or less 10 meters. So with a real data, with a real radar, real aperture radar, okay, on board of a satellite, we reach a resolution on the ground of tens of kilometers. So it's absolutely useless an image with tens of kilometers of resolution on the ground, because you have 14 for 14 the resolution of your pixel on the ground, and this kind of information, as you can imagine, is totally useless. So this is the difference with the synthetic aperture radar. With the movement of the satellite along the orbit, we try to synthesize a very, very long antenna, an antenna long kilometers. Okay, so we can see a target on the ground from a different position along the orbit, and it's possible to demonstrate. I have no time to show you all formulas, but you have to believe in me when I say that the resolution that you are able to reach with this kind of technique, with this kind of technology, actually, the synthetic aperture radar is only connected to the length of the antenna. So in particular, is half of the length of the antenna. So we move from tens of kilometers of real aperture radar to few meters of resolution, azimuth resolution, with a synthetic aperture radar. You can imagine how, and in particular, is totally independent from the distance between the radar and the target on the ground. So it's a very powerful thing of the characteristic of the synthetic aperture radar. So how it works? You can, with this slide, I show you. Yes, just a very an example of how it works. You have a satellite moving along the orbit. The satellite with the antenna acquire different image of the same area along the path along the orbit. We generate the so-called synthetic aperture, synthetic antenna, and as you can see here, using the characteristic of the sensor that is a coherent sensor, that means that we exactly know the phase of the electromagnetic wave that we transmit on the ground, we are able to join all this information, to combine all this information to generate a radar image like this. This is just the amplitude of the radar image, because the radar image is a complex image. So we have an amplitude and the phase. Here we can just represent the amplitude. This is the most beautiful place in the world. This is Napoli Bay Area, where I live. Okay, this is an image that we can represent with the amplitude and with the resolution of just a few meters. So how this kind of satellite work? Essentially, this kind of, as you can see in this video of ESA, we have this satellite orbiting in usually the satellite that we use, but it's not only we have not only one possibility. We have this kind of orbit that are known as polar orbit. So the satellite moves from north to south and from south to north. The Earth turn under the satellite, and so in this way we are able to have an image everywhere on the Earth. Okay. So when we work with satellite, a synthetic aperture radar on board of a satellite, we have two kinds of acquisition. In this configuration, a polar orbit configuration, we may acquire an image of ascending orbit. So when the satellite moves from south to north, and a descending acquisition when the satellite moves from north to south. Okay. When now it's important to focus on the geometry of the radar, because as you can see in this slide, if we have a displacement on the ground, okay, the green arrow in this slide, and that is as composed by two components, for example, in the plane east-west and vertical, so the sky blue for the vertical one and the brown for the east-west component. Essentially what we see with radar is just a projection, a one-dimensional. We have an information that is the displacement in our case is a three-dimensional information, because we live in a three-dimensional space. So the displacement is on east-west, north-south, and vertical component of the formation, while the radar just see a one-dimensional information, the so-called line of sight. So we see when we have an image of a radar image, the projection of the displacement along the line of sight. And as you can see, dependently of the movement, the projection, the line of sight for ascending is the red arrow, and on descending is the blue one, can be totally different, because the projection depending of the acquisition geometry, and ascending and descending orbits have different acquisition geometry. So we move from a three-dimensional space of the deformation where we live in a one-dimensional space. We have all information encapsulated in one information, the line of sight. Okay, with just one radar image, we have yes, several problems, because okay, it is possible to detect the distance between the sensor and target. It's possible also to have information about the position of the pixel along the orbit, but we are not able with just one acquisition to discriminate essentially 2 points that have a different height, just only because these 2 points can have a same distance between with the radar. Okay, to solve this ambiguity of the of a radar acquisition, we need to move from one acquisition to a couple of acquisitions, a radar acquisition. 2 acquisitions with a specific baseline, so distance between the 2 acquisitions, we are able to detect also the height of the height of a pixel on the ground, as you can see in this pictorial, let me say, slide. So by using these principles, okay, we can essentially have several configuration of the radar. Okay, in particular, we can have the across-track configuration. Essentially, when we have 2 acquisition, 2 image acquired from 2 radar image acquired from different position, but in the same time. And after I show you some example. We can have a configuration known as a long track configuration, when you have 2 acquisition from exactly the same position, but in 2 different time. Okay, a long track configuration, and then our case, satellite synthetic aperture radar, satellite synthetic aperture radar for the technology, use essentially a combination of both these 2 configurations. So we talk about across a long track configuration. The first configuration, the cross-track configuration, okay, you have 2 acquisition, S1, S2, in the same time with a baseline, so a distance between the 2 antenna, let me say, that catch echoes of the same scene on the ground, and using a very important parameter, that is in particular the perpendicular baseline, in other words, the projection of the baseline orthogonal to the direction, to the fly line, let me say, to the orbit, we are able to detect the topography, the height of the pixel on the ground. Okay. This is an example of a radar in a cross-track configuration on board of an airplane. Okay, you can see here better in this image. You have 2 antenna, okay, that acquire in the same time an image, the electromagnetic echoes. So an image, we have 2 images in the same time, but from different positions. As you can see here, this distance between these 2 antennae is the perpendicular baseline. And this kind of configuration is used to generate the so-called digital elevation model, because we can retrieve information about the topography of the scene. Okay, this is the same configuration. Everyone knows the shuttle radar topography mission, SRTM mission. Okay, this mission was done in this kind of configuration. The shuttle had a main antenna in its belly, okay, that was also the transmitter, okay, and then had also another antenna along this very long arm, 60-meter arm, okay. So we have 2 antenna that acquire 2 images in the same time from different position to generate a digital elevation model. Okay, this is the cross-track configuration. The second configuration is the long track configuration. So you have from the same position to acquisition S1, S2, but in different time. Okay, in this configuration we have no baseline, okay, because it's exactly in the same position. So we have no information about the topography, okay, but we just can have information about what is changed during the two acquisition. So the displacement on the ground. Okay, this is a real example. Okay, you have two antenna on board of an airplane. Okay, the antenna is essentially on the same position along the orbit. Okay, along the flight path. Let me say, but we acquire an image in this time here, and just after fraction of second we acquire another image. Okay, this kind of configuration is used, for example, for this in this way with the airplane to detect displacement, very fast displacement. For example, the movement of the wave of the sea, or for example, the fast movement of the glacier. Okay. So let's move to our case. We work with the synthetic aperture radar satellite configuration of synthetic aperture radar. So the satellite moves in an orbital tube. Okay, so it's not possible to pass exactly from in the same positions. So we have a baseline. So we have different acquisition from a different position. Okay. And a radar, a satellite, works in this way. We acquire an image now, and then acquire a new image after 3, 6, 12, 24 days, depending on the constellation that we use. So we have the so-called across a long track configuration. So in this configuration, we are able to detect also, we have information about the topography, and we have also information about the displacement on the ground. Okay, so this is essentially the configuration, across a long track configuration. So the high of the topography, as you can see, Z here, and also the displacement on the ground. Okay, how it works? The synthetic aperture radar on satellite, and how the differential SAR interferometry works by using and combining two acquisitions. Essentially, we have the radar, okay, acquiring an image in a specific time T0 of Napoli Bay Area. This is just an example, okay, in T0. Then after, for example, for Sentinel-1, that you probably know, after 6, actually now 12 days, we have a new acquisition from a different position. So we have a baseline between the two orbits. We can combine these two complex image, this radar image. We can extract the phase of this combination to retrieve the so-called interferograms. Okay, the interferogram, from the interferogram, and after I show you how to do this, we can extract an information about the movement on the ground. Okay, this is the only one formula that I show you that is very easy, just to show you the interferometric phase, what is connected to the interferometric phase, which component are encapsulated, let me say, in the interferometric phase. Essentially, we have two information, as you can see here. One information here that is the topography phase, that is only connected to some parameters, geometrical parameters, so the baseline and several angles that depend from the acquisition geometry of the radar. And then we have the deformation phase that is directly connected to the displacement projected in line of sight. Okay. So it's quite easy to demonstrate essentially that this contribution that is only connected to a geometry, this is only geometry, we can remove, okay, in a very easy way, this contribution, okay, to retrieve only information about the displacement. When we generate an interferogram, starting from two synthetic aperture radar acquisition and combining these two acquisition, extracting the phase, we are able to retrieve an interferogram. This is an aspect of interferograms. The interferograms here, probably you usually know another kind of interferogram after I show you, but this is an interferogram with topography and displacement, with the phase that encapsulate topography and displacement. Okay, this high rate of fringes essentially is due to the flat Earth, essentially, so to the topography that we are able to estimate by using an external information that is a digital elevation model projected obviously in line of sight of the radar. So removing this component of topography from the interferogram, we are able to retrieve a differential interferograms. So we need to discriminate what is an interferogram and a differential interferogram. The differential interferogram is when we remove from the interferometric phase the phase directly linked to the topography information. Okay, so this is an interferogram. Probably, usually you see this kind of information here that are differential interferograms, and by generating the differential interferogram, we have also another important information that are used in DInSAR application, that is a coherence map, that is essentially a map that gives us a noise level of the phase. Okay, so a correlation, a spatial correlation and robustness of the phase extracted from the interference. Okay, so this is a differential interferograms generated over Napoli Bay area. This area here in the white square is Campi Flegrei caldera. As you can see, there are some fringes here connected to the phenomena of bradysism of Campi Flegrei. This is an interferogram generated in March, July 2000, when the Campi Flegrei was in a subsidence phenomena period. Actually, now, as you probably know, everything is changing. Okay, so the deformation phase is possible to demonstrate that is directly connected to the wavelength. In particular, the fringes are connected to the wavelength, and from a fringe to another fringe, from a mathematical point of view, means that there was a movement or something changed between the master and the slave acquisitions with an entity of half a wavelength. Okay, so if I move from this blue here to this blue here, we have, this is ERS image, so C-band, so we have a wavelength of 5.6 centimeters. So from blue to blue, we have 2.8 centimeter detected by the technique. That means something is changed of 2.8 centimeters. So if we move from this blue to this blue and then from this other fringe here, we can estimate essentially the displacement that in these 4 months corresponds to more or less 6 centimeters. So moving from we can move from a rapid expression of the phase, okay, that is expressed from minus pi to pi, because you know the mathematical expression of the phase is automatically constrained between minus pi to pi, okay, to centimeters. Okay, the blue line represent the phase, the interferometric phase in this natural representation constrained between minus pi pi. So you have, when you move to minus pi to pi, you have a fringe, then you have another fringe when you move again from minus pi to pi, and so on. but we need to reconstruct the displacement, okay? So we need to estimate the centimeter, okay? So in a continuous field, the displacement, okay? So we want to retrieve, let me say, the green line, okay, the displacement. To do this,
so
we need
3 minutes.
3 minutes only?
Yeah.
Okay, good. So we can move from this rapid interferogram to the unwrapped solution, so to radians to centimeter, by performing the phase unwrapping step, that is a very crucial aspect of our technique, because yes, we need to estimate the multiplier of 2 pi to add to the phase to move from a wrapped phase constrained to minus pi to pi to centimeter, or to actually to a continuous phase. Okay, so this is an interferogram of an earthquake, very famous earthquake in Italy, Aquila, in 2009. Okay, so we can move from this representation, constraint to minus pi pi, so a differential interferogram, by performing a phase unwrapping step to unwrapped phase, so to centimeter. Okay, so we move from this wrapped phase to minus pi pi to centimeter, representing, for example, here in this image, that means that this red area here means that something moved away from the radar, okay, and the blue area here, that something move toward the radar, because I want just to stress this aspect. We just estimate a relative movement of the pixel from the ground to the radar in line of sight, not the east-west or vertical. We can do this, yes, but applying several algorithms that after, if I have time, I can explain you. Anyway, this is just an example, but just to stress this aspect, with differential interferometry, if we have a soil here, okay, a representation of the ground, and if we have an image acquired in pass 1, okay, then after several days, we have another image of the same area, pass 2. And during these pass 1 and pass 2, we have, for example, a subsidence phenomena, okay, as you can see. We want to estimate this quantity here, that is essentially the extra path of the electromagnetic wave to reach the ground. Okay, this is the information encapsulated in the differential interferometry, in the phase of differential interferometry. Okay, this is another example. Okay, this is Etna volcano eruption 2018. Okay, this is a very fantastic interferogram. Okay, and this is the fringes due to the movement of the volcano, and this is the unwrapped phase, so centimeter. This is acquired along the descending orbit. This edge of the volcano go toward the radar. This edge of the volcano along the go away from the radar along the descending orbit. The same event is cached also over an ascending orbit, and the information changed because in this case this edge of the volcano go towards the radar, and this edge here, okay, go away from the radar. Okay, we can combine two differential interferograms to generate also, as I said you before, the vertical displacement and also the east-west displacement, but only combining two information, an ascending interferogram and descending interferogram. Okay, so to conclude, I want just to show you two slides about the advanced differential interferometry. Okay, with differential interferometry, we are just able to detect a single, to catch a single movement occurred between a primary image and a secondary image. But actually we have a data set, a big data set of images, and we can combine in a different solution all these images to generate a big stack of interferograms. Okay, and so we can combine all these interference with a specific technique. In particular, at CNR, IREA CNR, we developed a very famous technique that is a small Bayesian subset algorithm. With this algorithm, we combine all these differential interference to generate the so-called displacement time series. In other words, for each pixel on the ground, the coherent pixel, we can retrieve the temporal evolution of the deformation of the ground. Okay, this is a time series over Campo Flegrei caldera between first years of 19th to 2010, and you can see for this pixel here in Pozzuoli city, how the movement on the pixel along these 20 years of acquisitions. Okay, so this is just another example. This is Mauna Loa in Kilauea volcano. Okay, and so this is the eruption of Kilauea. Okay, and agreement with GPS, the green stars is very high. So to demonstrate essentially how this technique can be very powerful, because okay, with GPS we have a good accuracy. Okay, but with the DInSAR technique, advanced DInSAR technique, you have a very you can reconstruct, because you have a lot of pixels, the full displacement pattern. Okay. And another example is over Los Angeles Bay, that is, let me say, wonderland for the interferometry, because you have Newport Inglewood Fault, you have Santana Basin, you have Pomona with the oil extraction. Okay, so you can retrieve also the, for example, for Santana Basin, the seasonal behavior of the formation due, for example, to the recharge of the basin, and also during the summer, for example, the subsidence due to the extraction of the water, and so on. So I conclude my presentation. Just yes, it was a rush to compress all in just 50 minutes, but just I want to give you an overview about how this technique, the DInSAR, and in particular advanced DInSAR, satellite DInSAR, can be very useful for several applications, and in different scenarios, not only displacement, but also for other applications.
Let's now see a demonstration of the P-SBAS for Sentinel-1 on-demand service hosted on EarthConsole.
First of all, we select the SBAS service for Sentinel-1 in the P-Pro on-demand interface. I would like to point out the SBAS service for Envisat is also available, which is part of Heritage Mission Virtual Lab. We select an area of interest, for example, above the Napoli area. And we also select the start and date for the catalog search. It is advisable to start no earlier than 2016. We also move the reference point that will be used for files unwrapping to an area with high coherence and stable, for example, an urban area. At this point, we can start the search. Now we can restrict the search to a particular relative orbit. For example, the orbit 44. Now we select the product. We suggest to put here an appropriate number of results. And so on. We can assign the name of the jobs. The reference point is already set, and then we can submit our job. You can find the jobs running already done in my task tab. And for example, it's possible for a task already completed, it's possible to see the information, input data, parameter, output, and here it's possible to download the results. I would like to show you the result of similar task that I have already performed. The processing takes about 1 day. The result contains several data, as well as a map that can be imported into Google Earth. The areas in green are stable zones, while in red are highlighted subsidence phenomena, and in blue are areas where the land has arisen. For example, the Campi Flegrei. The actual data is contained in a comma-separated value file. Results are provided in line of sight. The process information is reported. For example, the acquisition dates of the images used. And then, for each measurement point, are reported the geographic coordinates, the topography above the ellipsoid in meters, the mean deformation velocity in centimeter per year, the temporal coherence, and the acquisition geometry, components of line of sight, unit vector along the north, east, and vertical directions. And finally, line of sight displacement time series in centimeter. Starting from the value 0.
We are in the position to offer free access to the P-SBAS for Sentinel-1 on-demand service via the ESA Network of Resources. This is an initiative by the European Space Agency aimed at supporting the use of cloud platforms for Earth observation data exploitation onboarded in this framework, such as EarthConsole, by covering the related cost. You can apply for an ESA sponsorship if you are working on a research project, an educational initiative, or a pre-commercial and demonstration project. If your application is approved by ESA, you will receive a voucher which amounts to maximum €5,000 for non-ESA project, while there are no limits if you are working on an ESA-funded project. The voucher will cover a 6-month subscription to the P-SBAS for Sentinel-1 service, including up to 500 processing hours. If you want to access P-SBAS for Sentinel-1 for free, you can visit our website and fill in the PPRO on-demand form on our web app by selecting the P-SBAS for Sentinel-1 service. Once you will submit your service request, we will review it and help you prepare a sponsorship request for your project to be submitted to the ESA Network of Resources. For any clarification, don't hesitate to contact us at info@earthconsole.eu. We would be happy to help.